In this video, we will discuss pumping lemma for context-free languages. Now, pumping lemma for context-free languages is used to prove that some languages are non-context-free languages. Now, to prove the pumping lemma, the grammar, which is context-free grammar, should be in Chomsky normal form. Now, the statement of the theorem is that if we have a language L, then there exists a constant n which is dependent upon the grammar, which is also called pumping length. Suppose we have the string z which is derived from the language L, and the length of the string is greater than or equal to n. Then this string can be subdivided into 5 portions: U, V, W, X and Y, with the following conditions, in which length of V and X should be greater than or equal to 1. Second condition is length of VWX should be less than or equal to n. And if these are the conditions, then for all I greater than 0, then if we pump the portion V and X, means if we increase the values V and X, then if this string is in this language, that means the language is context-free language. If after pumping the string does not belong to the language, that means this language is not a context-free language. Now, here we need to show that this we should be able to derive the string in this form. First of all, we should be able to prove that the grammar derives this string in this form, and we should be able to pump these two portions. Now, to prove that we should be able to pump this portion, we should have the rules of the form A tends to V A X. If we have a rule of such type, then on using this rule repeatedly, if we use this rule repeatedly, then obviously what will happen? We will have V to power I and X to power I. Means with the help of this rule, we will be able to pump V and X. Now we need to prove it. Now proof is, suppose we have a grammar G, which is context-free grammar, and context-free grammar is in Chomsky normal form, which generates the language L. Now, suppose that the grammar contains k number of non-terminals. Then, if we have k number of non-terminals, then the value of n, this constant n, will be n is equal to 2 raised to the power k. Then, let z be the string, and we take that the length of the string is greater than or equal to n. Now, for any parse tree which drives the string z, then the depth of the parse tree must be at least k. Now, we have taken that the grammar is in Chomsky normal form. So, we can consider the parse tree as a complete binary tree. Okay, cause in Chomsky normal form we have a rule of type A tends to X, Y. Means every non-terminal is producing two non-terminal portion, and through these non-terminal portions we can derive the subtrees. Okay, so if the grammar is in Chomsky normal form, then we can consider the parse tree as a complete binary tree. Then we have seen that if the parse tree has depth I, here depth means the level, the height of the tree. Okay, so if the depth is I, then the maximum length of the string generated will be 2 raised to the power I minus 1. Now to prove this, we use the induction method. Now what is induction method? According to induction method, we prove something for the base value. Then we consider that the theorem is true for n minus 1 values, and then we prove that for n values. Okay, so now here we need to prove that if the depth is I, then the length of the string derived will be 2 raised to the power I minus 1. Here we are taking the base value as I is equal to 1. Now check it for the base value. Now if I is equal to 1 means if depth is equal to 1, that means the structure of tree will be like this. S tends to A or S drives A. Here the edge is 1 or the depth is 1. If depth is 1, then length of the string generated will be 2 raised to the power I minus 1. Here the value of I is 1, means 2 raised to the power 0 is equal to 1. Means the length of string generated is 1, and here we are generating single terminal string only, which is of length 1 only. Now we can check it for I is equal to 2 also. If the depth is 2, means number of edges are 2, then the structure of the tree will be like this. Here also, if depth is 2, then the length will be 2 raised to the power I minus 1, means 2 raised to the power 2 minus 1 will be 2 raised to the power 1, which will equal to 2. So the length of string generated will be 2. So here we are getting the length of 2 terminals. Okay, now we assume that this is true for n minus 1 values. Okay, now for this, consider this tree. This is a pass tree where S is the starting point, or we can say it is the root node. Now from S, the depth of this entire tree is I. So obviously the tree generated from A is T1 will be having the depth I minus 1. Similarly, the subtree T2 will also have the depth of I minus 1. Now we consider that the theorem is true for I minus 1 values, means the string generated by this subtree, the length of string should be 2 raised to the power I minus 1, where I is the depth. So the string generated by T1 tree, length of string generated by T1 tree will be 2 raised to the power I minus 1. Here I am, instead of I minus 1, here I am having I minus 1 minus 1. So it will become 2 raised to the power I minus 2. Similarly, the string generated by tree T2 will also be the 2 raised to the power I minus 2. So the total length generated by this tree will be, length of Z will be length of Z1 plus length of Z2. So it will become 2 raised to the power I minus 2 plus 2 raised to the power I minus 2. It will be 2 into 2 into I minus 2. Then the length of Z will be 2 raised to the power I minus 1. Hence proved that if we have depth I, then the length of a string generated will be 2 raised to the power I minus 1. Okay. Now, the length of a string is, here we have taken that the length of a string is mod this. Length of a string Z is greater than or equal to n. Now what is n? N is 2 raised to the power k, where k is the number of non-terminals. Okay. Now Here we have taken length z greater than or equal to n. That means length of z is greater than or equal to 2 raised to the power k. Then obviously it will be greater than 2 raised to the power k minus 1 also. Okay. So if length of z is equal to 2 raised to the power k minus 1, then the depth should be at least k. If we are taking the length greater than this, then obviously the depth should be k plus 1 at least. Okay. Now if we have, this is the path length or depth. If we have k plus 1 depth, or depth, what is depth? Number of edges. Okay. So if we have k plus 1 number of edges, then the number of nodes will be k plus 2. Okay. Now if we have k plus 2 nodes but only k non-terminals, okay, nodes are k plus 2 and non-terminals are only k, then obviously on the path some non-terminal will appear twice. Okay, suppose we have a non-terminal A, we have k plus 2 nodes but the non-terminals are k, and one of these non-terminals is A, then obviously this A will appear twice, or any non-terminal may appear twice. Now suppose we have this parse tree generated from this root node S. S is the starting symbol. Now suppose we have a path length P. This is the longest path we have in this tree. Then we will be having two nodes V1 and V2 with the following conditions, that node V1 and V2 both have the same non-terminal. Okay, here we are considering that A is the non-terminal. Node V1 is closer to root node as compared to node V2. And the third condition is that the length from V1, node V1 to the leaf node should be k plus 1. So if the length is k plus 1, okay, and we have k non-terminals, then only one non-terminal will appear twice. Okay, so we have taken that A is appearing here twice. Now consider it that here this is a structure of this tree. Now look at this. From V1 we are able to derive a string, say Z1, and from node V2 we are able to derive a string, say Z2, and from V1 at the left hand side some string Z3 is generated, and at the right hand side some string Z4 is generated. Then we can write Z1 as Z3, Z2, Z4. This is the rule. Okay. Now here we have considered that the grammar is in Chomsky normal form. Chomsky normal form have the rules of type like this. S tends to XY, means at the left hand side single non-terminal, and at the right hand side we have two non-terminals. Okay. Now starting with this V1, and if we derive this V2, then obviously with this rule this V2 will fall either to the left hand side of it will fall either to the left subtree or to the right subtree. Now I have taken these cases. Suppose this is V1 and this is V2. V1 generates some string and V2 generates some string. Now V1, suppose the V1 generates a string Z1, and Z1 can be written as Z3, Z4, Z3, Z2 and Z4. Now from V2 we are able to derive Z2, but no Z3 is appearing here, only Z2 and Z4 is there. So in this case V2 is lying in left subtree, so Z3 is empty here. Now look at this condition. V2 is lying in right subtree. So in this case we have Z3, Z2, but we don't have Z4 here. So in this case Z4 is empty. Or we may have this case that Z2 is lying in between. Some portion is generating as Z3 and some portion is generating as Z4. So this may be the situation that either Z3 or Z4 may be empty, but not both Z4 and Z3 may be empty simultaneously. Okay, so that's why we have taken the first condition that the length of Z3 and Z4 should be greater than or equal to 1. So this belongs to first condition, that length of V and X is greater than or equal to 1. Now next is that the length or depth is at most k plus 1 from V1. That means the maximum length generated will be 2 raised to the power k, which is nothing but equal to n. That means we have taken this condition. This is the second condition of the theorem, that length of VWX should be less than or equal to n. Okay, so we have proved why we have taken these two conditions. Okay, now look at this tree. Here from A we are able to derive Z1. Okay, and Z1 can be written as Z3, Z2, Z4, or we can write it as Z2 is derivable from A. So we can write it as that A drives Z3, A, Z4. Okay, so we have this rule. Finally we have this rule that A drives Z3, A, Z4. Fine. Now if we use this rule repeatedly, that means we are able to pump this portion Z3 and Z4 simultaneously. That was required to prove the pumping lemma theorem. Now here we can pump Z3 and Z4 I number of times or any number of times simultaneously. Now suppose according to the theorem we take Z3 is equal to V and Z2 is equal to W and Z4 is equal to X. Now from this tree here we are able to derive from S this following string, and this string is V, Z1 and Y. Okay, and look at this, Z1 is derived from this non-terminal A. So we can have this rule that S drives U, A and Y. So that's why we have this rule, S drives U, A, Y. Now look at this. Here we are able to derive A drives, as we have seen earlier, that A drives Z3 to power I, A, Z4 to power I. Now if we put the values Z3 as V, Z4 as X, and here we have Z2, and Z2 is nothing but W. So we have this rule, A drives V to power I, W, X to power I. So if you put this value A in the previous rule, this, S tends to U, A, V, then the final rule will become S tends to U, V to power I, W, X to power I, Y, which was required format. So hence we have proved the pumping lemma for the context-free language. Now, to prove whether some language is context-free or not, what we will do? We will subdivide the string in this format, okay, in the U, V, W, X, Y, and then we will pump this portion V and X. Now, after pumping this, if this string belongs to language, that means the language is context free, otherwise the language is non-context free. Okay. Now let's take an example that L is equal to A to power n, B to power n and C to power n, where n is greater than or equal to 1 is not a context free language. Okay. Now as we know that if some language holds pumping lemma, that means the language is context free. If it does not hold pumping lemma, that means the language is not context free. Now first we consider that language is a context free language. Now if it is a context free language, that means it should hold the pumping lemma, right? Now take some string of the language. Language is A to power n followed by equal number, the language is, we have number of A's and followed by equal number of B's followed by equal number of C's. Suppose we take some string of A's, B's and C's. Now we take some string of this A to power n, B to power n, C to power n, which is the sequence of number of A's followed by equal number of B's and followed by equal number of C's. Now we divide this string into subparts in V, W, U, V, W, X and Y with this condition, means the length of V, W, X should be less than or equal to n. Here we have taken A to power n. Okay, the length of this should be less than or equal to n. That means that this portion V, W, X should reside either in A's or in B's or in C's. Okay, one case may be that either it may reside in A's or in B's or in C's, or it may happen that some portion of VWX reside in A's and B's, means this reside between A and B, or this string portion reside between C and B and C. Now if this portion resides within this A's and we pump the value of V and X, then what will happen? In this case, number of V's and X, if we pump this portion, then number of A's will be increased, but number of B and C will be the same. Okay, then what will happen? This string generated will not belong to the language. Fine. Now similarly, if this portion resides in B's only, then number of B's will be increased, A and C will remain the same. Similarly, if resides in C, then number of C's will increase and A and B will remain the same. Now if this portion reside within A and B, if it resides within A and B, then what will happen? That number, and if we pump the value of V and X, then the value of A and B will increase, but value of C will remain the same. Similarly, if the portion VWX resides within this B and C, then the value of B and C will increase, but the value of A will remain the same. So finally what we see, that this language u v to power x, u v to power I, w x to power I, y finally does not belong to L. Okay, in every condition that when we pump the value of v in x, then the string does not belong to L. So finally we conclude that L is not a context free language. Thank you.